Hello. You can hear me okay? Awesome. I'll start sharing my screen. Can you guys see the screen? Hi, Steve, I can't hear you.
Me now?
Yeah.
Yeah.
So it looks okay, I guess, and I just need to go to full screen.
Everything looks good. Yeah. Try full screen.
Yeah. So how does it look now?
It's still okay. I think the connection is a little bit slow, so I hope your animations, if you have any of them, render okay. But if not, we've got the slides offline as well.
Okay, if the connection ends up being a bit bad, I can connect to a different Wi-Fi and try if it's any better.
Do you want to try if you've got an animation, see how that comes through, and then we can judge.
Sure. You see a preview. Yeah, something like that. Oh, there's a bit of a delay, but
Yeah. I mean, we're seeing it. It's just a little bit uh, choppy. I think that's fine, Maria. And
okay. Okay, it should be okay. I'll try to go slow so my slides can keep up.
all right, I'll introduce you now and then we'll get started. So it's a pleasure this morning, or in Maria's case, early evening, to have Maria Carisi join us. She's a professor at Washington State University and IA Fourth at the University of Crete. She was previously a postdoctoral fellow here. She's an expert in all aspects of supermassive black hole binaries, and especially their electromagnetic signatures and searches in large time domain surveys for any presence of supermassive black hole binaries. So Maria is really interested in multi-messenger astrophysics and the possibility of a joint gravitational wave and EM connection of supermassive black hole binaries. She's going to tell us all about that connection today and her ongoing hunts for these multi-messenger systems. So Maria, let's give her a round of applause.
Thank you. Thanks, Steve, for the introduction. As Steve said, I'm going to talk about supermassive black hole binaries and focusing on how we can use time domain data to find these systems. I will describe why this has proven to be a very difficult problem. And in the end, I will discuss a bit the connections with pulsar time arrays. I will talk about multi-messenger prospects, and then I have also prepared a tutorial for you to play with some time domain data and try some periodograms and see what the challenges are yourself. You can interrupt me at any point, either writing on the chat, I'll try to monitor the chat, or by unmuting the room, I guess, and asking. But I have also some points that I will stop to make sure that if you have questions, I can answer those. So, of course, this is a gravitational wave school. You know that we live in a very exciting time. It has been over 10 years now since this very exciting first detection of gravitational waves, where we first saw two stellar mass black holes merging, producing a gravitational wave that we detected with the ground-based detectors like LIGO and Virgo. And this is a monumental time in astronomy, and it can be compared to the time that Galileo pointed his telescope to the sky and started to systematically observe the celestial objects like the planets. And in the beginning, we could see a very, very small part of the electromagnetic spectrum. We could observe only in the optical band. But then eventually, we developed the technology and we covered the entire electromagnetic spectrum from the most energetic phenomena in gamma rays down to the lowest energies in radio waves. And of course, that allowed us to get a much more rich and complete understanding of the universe. Now, of course, I don't have to give an introduction on what gravitational waves are in this audience. They're perturbation spacetime that are produced when we have masses that are accelerated. And the thing is, they're very, very weak. So if we want to detect gravitational waves, we want to have very extreme systems. So we want to have pairs of black holes or pairs of neutron stars because they produce stronger gravitational waves. And we know that the frequency these systems emit depend on the mass of the system. And the maximum frequency they emit, we could probably derive this very easily. It's inversely proportional to the total mass of the system. Now, in the universe, when it comes to black holes, we know that we have at least two varieties of black holes. Stellar black holes, stellar mass black holes that come from stellar origin, and supermassive black holes that have millions of times the mass of the sun, and these reside in the centers of the universe. So we know that in terms of black hole mass, there is a variety of black holes out there that span several orders of magnitude. Most likely they come in pairs. So we expect that we have gravitational waves that span a huge order of magnitude in gravitational wave frequency. And I'm sure during these last 2 weeks, you heard a lot about the gravitational wave spectrum. So I will just do the very, very brief overview of the spectrum just to situate where these massive black holes live. So we're looking at the spectrum in terms of the gravitational wave strain and the frequency. We have opened, the first thing we saw was high frequency gravitational waves. And now we had 4 observing runs by LIGO. We have found hundreds of binary black holes and a couple of binary neutron stars and of the 2 types. Then in 10 years, we will have LISA, which will be a gigantic interferometer in space. And LISA will be sensitive in millihertz frequency gravitational waves, and it will detect several different kinds of sources, like the most massive of the stellar mass black holes, the least massive of the supermassive black holes, extreme mass ratio in spirals, and many other binary systems. Now, this talk will focus on the supermassive black holes, the biggest ones we have in the universe. And these emit gravitational waves in the nanohertz band that can be detected by pulsar timing arrays. So the talk will focus on how we find these systems using electromagnetic waves and then how we can combine a bit with the gravitational waves to do multi-messenger science. So first of all, again, probably you heard some of this intro before, but why do we expect to have supermassive black hole binaries and why we care about these systems? I want to make sure we're all on the same page about this. So I know Jessie gave a lecture last week and she talked a little bit about that. So when we observe nearby galaxies, for example, this is our closest neighbor, the Andromeda galaxy. We see that in the center of at least the massive galaxies, there is a supermassive black hole. And when I talk about supermassive black holes, I really mean the very massive ones, the ones that have from less than a million, although typically a million, to several billion times the mass of the sun. So these are big, and we also know that they're very important for the host galaxy. Because there are several correlations that show that the mass of the central black hole is correlated with several properties of the host galaxy. So we know there's some sort of coevolution between the black hole and the host galaxy. So the black hole, even though it's small compared to the galaxy, it's very, very important for the life of the galaxy. The other thing we know is that in the history of the universe, we have galaxy mergers. And this is an animation. I know it will play a bit slowly. So we have two black holes, each one containing two galaxies, each one containing a black hole that collide, and they produce a post-merger galaxy that will have two supermassive black holes. As the merger progresses, the two black holes come to smaller and smaller separations. And when I will talk about binaries, I will refer to the stage when the two black holes are gravitationally bound one to the other. And that happens when the mass that is enclosed in the orbit is roughly equal to the mass of the two supermassive black holes. And then in terms of separations, that happens at the parsec scale. So when I talk about binary, I talk about systems that have reached the parsec scale and even smaller. So in galaxy mergers, typically there's also quite a bit of gas that is involved. So galaxies have stars and they also have gas. And we know both from simulations and from observations that when these galaxies merge, the gas will end up at the center of the post-merger galaxy. And this is very important because we have gas around the black holes. That means it can accrete onto the black holes and therefore produce bright electromagnetic emission. So this is important for looking for electromagnetic signatures around supermassive black hole binaries. We do expect, both theoretically and observationally, by looking at post-merger galaxies, that these mergers, at least some of the mergers, happen in gas-rich environments, so they can produce bright electromagnetic emission. So I know Jesse talked a bit about spectroscopic signatures. The idea there is the same. You have gas and there are broad emission lines that the orbit of the binary can be imprinted on the spectrum of the system. I'm going to talk about photometric searches. So it's a different method to find these binaries, and they probe slightly different separations. So actually, I have a slide on the evolution, but I know Jesse talked about it, so I'll probably skip it for now unless you have questions. So I'll just go to the observations directly. So we know now, we have very many observations of the initial stages of galaxy mergers. And over the past couple of decades, we have observed post-merger galaxies that have two active supermassive black holes separated by kiloparsecs. We have over 100 such systems where both black holes are active. They are called dual AGN. And they can be resolved across the electromagnetic spectrum. In fact, we have resolved such systems with X-rays, optical, infrared, radio observations. Now, when we go to even smaller separations, like the merger progresses and the black holes get to the binary stage, roughly the parsec scale that I mentioned before, it's very hard to just take an image of the galaxy and see the two black holes. Because the angular separation is very small. So the only technique that could work at this stage is to use very long baseline interferometry. That means using the entire Earth as a coordinated telescope. And that can work to the parsec scale, but if we go to even smaller separations, even that cannot work. Like the Event Horizon Telescope that took the image of the shadow of the black hole in our galaxy or in M87 doesn't have the resolution to see a milliparsec binary if the galaxy is beyond our local universe. So how do we find these systems? And again, Jesse talked about spectroscopic signatures, and I will talk about photometric signatures here. So one possibility is to look for quasars that have periodic variability. So first of all, why quasars? We think that the quasars, at least some of the quasars, are activated by galaxy mergers. So practically the merger perturbs the gas distribution and brings the gas to the center and it triggers the AGN. That means that quasars or AGN are very good hosts to look for two supermassive black holes. Now, why periodic variability? Again, I would say this is fairly intuitive. We have gas and we have a binary that periodically perturbs the gas. So we should expect there should be some periodicity in the behavior we see. But again, this is something we have seen in many simulations. So what happens when we put two black holes in a gaseous disk is as the binary orbits, there will be torques to the gas, and these torques will expel the gas from the central region, and it will create a cavity. So in the center, close to the binary, we will have a cavity that has very low density. And this is the black that you see here. But the good news for us is that this cavity is not completely empty. There's a lot of interaction with the edges of the circumbinary disk. And we have streams, which is these pink features here that enter the cavity. And we have these mini disks. So some of the gas ends up being bound, trapped around the black holes, and it moves with the black holes. So each of these features can give us a mechanism to produce periodic variability, and I'll try to go through the potential ideas. So first of all, when we have these streams, if we look at the accretion rate, so how these two black holes are fed from the gas that is around them, for example, if we have relatively low mass ratio systems, we see a prominent periodicity at the orbital period of the binary. So as the binary goes around, it pulls these streams inwards periodically, and we see significant periodicity at the orbital period. If we have a high mass ratio system, something between 0.25 to 1, then we see additional features. So we do see some periodicity at the orbital period, but the most prominent periodicity we see at lower frequencies. Why that happens is that as the binary orbits, these streams come in, but they don't always hit the binary. Sometimes they hit the opposite wall of the cavity. And we have the formation of an overdensity in the edge of the circumbinary disk. So what we end up seeing as the main periodicity is the orbital period of that hotspot. So we see that at a few times the orbital period. So periodic accretion and the formation of the hotspot can give rise to periodic variability. Now, another possibility has to do with what I told you about the formation of these mini disks. So, and that happens in systems that are relatively unequal mass. The two black holes don't have the same mass. And also the orbit is not too far from edge on. So there's a velocity component in our line of sight. So what happens in this case? Typically, the secondary mini disk is brighter because it's the one that moves closer to the edge of the cavity, and it's the one that perturbs the circumbinary disk more. So it's the one that pulls the material inwards. So it has a brighter mini disk. It's also the one that is moving faster. So practically, the variability here will be dominated by the mini disk of the secondary black hole. So when the secondary black hole moves towards the observer, it will be boosted. It will appear brighter. When it's moving away, it will appear dimmer. And that, as the binary moves around, it gives rise to periodic variability. Now, the periodicity in this case is at the orbital period of the binary because we practically see a light bulb moving back and forth. And this variability, this periodicity can happen even if the mini disk has constant luminosity in the rest frame. Now, the amplitude of that periodicity depends on a few things. It depends on the inclination of the system and the velocity of the secondary, which in turn depends on the mass ratio and the period and so on. So by measuring the amplitude, we can also have some constraints on the properties of the system. And you will see then in the connection with the gravitational wave signal, that becomes important. Now, the last possibility is that we have a low mass ratio system and again, a system that is not very inclined. So the binary moves almost close to our line of sight. So the mini disk of one black hole at some point will go behind the other black hole and the light will be lensed from the other black hole. So in that case, we have lensing flares that repeat twice per orbit. So the most prominent flare is usually when the brighter mini disk of the secondary is lensed by the more massive primary black hole. So we see these very prominent flares once in orbit. But we can also have a secondary flare when the big black hole goes behind the small black hole. So we have very sharp and symmetric features that we expect to periodically repeat. Now, the bottom line of this story is that we do expect that binaries are associated with quasars. And we see from simulations that binaries can produce bright electromagnetic emission at the quasar level. And that emission is periodically modulated. And I described the different possibilities of producing periodic variability. And because I saw that I'm running out of battery, you will give me a second to connect to my power cord. So I'll be back in a minute and see if you have any questions about what I have talked so far. So give me a second. Okay, I'm back. So are there any questions about the mechanism of use variability?
Thank you. Oh, is there questions? Sure. Yeah, Sam, go ahead.
Hey Maria, can you hear me?
Yeah.
So talk about the periodic accretion, right? What are you looking like? What happens in the power? You're looking at this in the optical spectrum, the optical band.
Yeah, so most of the searches have focused on optical, but the prediction can be from X-rays to infrared.
And what about radio? Like you can have radio emission of jets if the accretion is high enough. Does that happen?
Yeah, so there's a few things. One is that you periodically feed the jet and you could see some translation of that periodic accretion in the jet. There's also, I will talk a bit in a few slides, you have a jet that is moving, right? One of the black holes that is associated with the jet is moving with the binary. That means that you won't have a straight ballistic jet, but you will end up having a helical or somewhat distorted jet. So yes, there are possibilities of seeing one, periodicity in the jet, and two, seeing the morphology being disturbed. Are there any other questions?
I think you can go ahead, Maria.
Okay, sounds good. So now I'm gonna try to cover what we have done so far to look for periodicity in the data and why this is a hard problem. So in the last 10 years, we had a lot of developments in the search for quasar periodicity. And the reason is that over the last 10 years, we had time domain surveys. These are telescopes that systematically scan the sky and come back to the same part of the sky over and over, and they record how the brightness evolves over time for millions of sources. And you can see I have listed here the big systematic searches in different time domain surveys, like the Catalina time domain survey, the Palomar Transient Factory, Pan-STARRS, the Dark Energy Survey, Zwicky Transient Factory, Gaia. These are only the optical ones. And you can see how big the samples are and how many candidates we have seen in each case. And the same exercise, we've done it with different time domain surveys in infrared, for example, from WISE, or in X-rays with SwiftBAT, and there are a few additional candidates. So as you can see, we have now hundreds of candidates, and I'll just show you some examples. So here are some examples of, these are light curves. So practically what you see is the magnitude or some measure of the flux of the brightness and how it evolves over time. And these are just some of the few examples of how these quasars look. And there are also some that have been detected individually. So these are how the light curves look like. But we know now that a lot of them, and maybe all of them, are false detections, because finding periodicity in quasars, it turns out it's a very challenging problem. So for the next few slides, I will try to explain why this is so hard. One of the reasons is that typically the periods that we are looking for are years long, so a few years long. And the baselines we have, again, are a few years long, so we cannot see the repetition of the periodicity many times within the data. So there is this relatively simple solution. We can keep monitoring the same system and see if the periodicity is persistent. Like if we can observe many, many cycles, we can build our confidence that we are really looking at the periodic system and we are not looking at an artifact of the noise. So, for example, and of course, the other solution is that we go back to the archives and see if we have additional data for the same source to test whether the periodicity is persistent back in the old data. Usually when you look at older data, you end up with more noisy data, so it's not always the easiest thing to exclude some candidates or confirm them. But several of these studies looked at one time domain survey. They analyzed the data. For example, this is from my thesis work in PTF. So the PTF data were the red the data points. We found 50 candidates, and then we expanded the baselines, and we looked whether the periodicity was persistent, and we managed to exclude some of them. Again, the same history more recently with the ZTF data. You can see the ZTF data are the orange here. They have very good quality. This study looked at 4 years of data. They found about 127 candidates. And then they looked at Catalina and other historical data, which you can see they're more noisy. And again, they managed to exclude most of the candidates. And there was another recent paper. There was a study that looked at Gaia, which is a satellite. So it has very good photometric quality. They found about 180 data candidates. A lot of them had noisy ZTF and Catalina data before and after. And they managed to exclude a lot of the candidates again in this case. So this is a relatively simple solution. You either look longer or you go to the archives and see if you have other data. The problem is because the periods can be a few years long. If you want to accumulate enough cycles, you may need to wait for decades. The other problem is that these binaries, we expect them to be more common when they have these long periodicities. So it's much more likely to find a binary that has a period that is 5 years than one that has 5 days. And in that case, you can accumulate many cycles. Now, one of the biggest challenges, which is not completely obvious if you're not working with quasars, is that quasars have red noise, and this is why we have a lot of false detections. So what does it mean? And again, in the tutorial, I put some things to get your hands dirty with the red noise. So in this figure, we have the data from one of the most prominent candidates. I think this is PG1302. It's the first one that was detected. So here are the scatter plot is the data that were used to detect this candidate. And you can see that we have a couple of cycles. And then on the back, you see a pink line. And that pink line is simulated quasar noise. So this quasar is a typical quasar. It has one supermassive black hole. And then when you simulate the noise, you can see that when you have just 2 cycles, it can look very periodic. So it's very hard to differentiate periodicity from the red noise because the noise can mimic this oscillatory behavior. So most of the searches that I showed you, the candidates, they used what we call a dumb random walk model. So you will have the chance to play a bit with this model in the tutorial. But very briefly, this is a 2-parameter model. So practically, at the low frequencies, this looks like white noise, completely uncorrelated when you look at data points that are far apart in time. But when you look at timescales that are short, this noise is red noise. So this depends on the frequency. The power spectrum of the noise has this form here. And you can see there are 2 parameters. One is sigma. This determines the amplitude of the noise. And tau, which determines where this break from the red noise to the white noise happens. So we have red noise, which practically means that the noise is frequency dependent. White noise has a power spectrum that is just flat. And this dumb random walk model, which is used a lot, is successful to model the optical variability with the quality of data that we have from ground-based surveys. Now, there have been studies that used better quality data. For example, Kepler, that detected a lot of exoplanets, was a space mission and had amazing photometric quality, amazing cadence. It was observing very frequently, staring at the same part of the sky all the time, no gaps. And then there were a few AZN, not that many, like a couple of dozen in that field. And people analyzed the power spectrum of those, let's say, dozens of AGNs. And a lot of them show deviations from this dumb random walk model. So now the field is moving towards more complex models like the dumb harmonic oscillator or continuous autoregressive mean average models. They're called karma models. Both the dumb random walk and the dumb harmonic oscillator fall under this category. And we are developing more flexible models to describe this quasar variability. And the thing is, the better you know your noise, the more reliable are your statistics, and the more reliable are your periodicity detections. Another possibility that we worked out with the student is to try to ignore the noise, like come up with a way to assess the periodicity significance, but being agnostic about the noise. So practically, when we look for periodicity, we have, or a signal in general, we have a test statistic, and then we are trying to assess how often the noise can produce the test statistic. In our case, it could be the peak of a periodogram or a Bayes factor or something like that. And then your success depends on how well you know the noise. In this case, with the student, we came up with an alternative way. So we take a periodic template and we squeeze it and stretch it. So we make a template that is oscillatory, but it's not periodic. So anything that will trigger on this template is by default a false positive. So that gives us a way to assess the null hypothesis without making any assumptions for the noise. So for example, here we used as a test statistic the Bayes factor, which compares, for example, periodicity versus dumb random walk. And we calculated on the PTF data the Bayes factors for all the quasars. And you can see in some cases we have very high Bayes factors, so we would say we have significant periodicity. And then we do the same thing, but instead of using the periodic template, we use this null signal template, and we calculate the same Bayes factors. And you can see that we get even higher Bayes factors. So the null template gives us higher Bayes factors. That means we don't have any significant candidates. So the red noise is a big problem in general because it introduces a lot of false detections. It turns out that because we have this type of noise, it's also very easy to miss some of the real periodic signals. So all of the searches I described, they focused a lot on finding sinusoidal periodicity. And this is very simple. We have very efficient tools for finding sinusoidal periodicity. It was a no-brainer to search for this type of periodicity in the beginning. But we know from the simulations that sinusoidal periodicity can happen in a small part of the parameter space. So we have, for example, relativistic Doppler boost in a circular binary. Most binaries will produce more complex periodic profiles. So if you take the periodogram, which again, you will have a chance in the tutorial to play with, and you inject a sinusoid, you get a huge peak, for example, and then you inject something that doesn't look like a sinusoid. It's maybe a sawtooth, which is what we expect from simulations, and you see that the peak of the periodogram is reduced by quite significantly, in this case by 40%. So the question is, since we use this type of analysis very often, can we find the non-sinusoidal signals in the data? So we did a study where we injected both sinusoidal periodicity and sawtooth periodicity on top of the dumb random walk noise that I was describing before. And we determined how many we could recover, whether it's sinusoids or sawtooths. So for example, for the sinusoids, we can recover up to 40% of the injected signals. But then when we look at the sawtooths, which again are likely more common, we detect less than 10%. So even if we have this type of periodicity in our data, because we have red noise, and because we use tools that are not optimized for searching non-sinusoidal periodicity, we may miss a lot of the signals. So this is quite a big of a problem. We started developing some solutions. So for example, using Gaussian processes, and instead of using a sinusoidal kernel, we use something that is more flexible. Here are, again, simulated idealized data, both sawtooth and self-lensing flares. And we fit them with the sinusoidal template or the quasi-periodic template that is more flexible. And you can see when we fit them with the sinusoid, we can recover the period data, most of it. So in terms of periodicity significance, this is very low. But then when we use the more flexible kernel, it starts to recover the shape of the periodicity. In that case, it becomes a more significant detection. So we start to build solutions that will allow us to find these more complex signals. The problem is typically these solutions are very slow. So for example, in another study, they were looking for self-lensing flares, again with simulated data, and they used templates. So you produce the analytical forms of how these flares should look like, and you go through the data and you see whether you can recover them. The answer is yes, to some extent. Both of these methods are very slow. Now, we started to develop a very large suite of simulations to pretty much test our algorithms to prepare for LSST. And of course, so far, I talked about time domain searches and how we can use this quasar periodicity, but binaries could probably produce a variety of signals and also produce them at the same time. So looking for additional signatures, and I kind of mentioned these jets, the radio jets, if we could have a candidate that has several independent lines of evidence, like we have periodicity and we have spectra that shift back and forth, and we have distorted jets, or we see the photocenter moving back and forth, then we can start believing this candidate. So in this figure, we have collected all the significant signatures that people have looked to find binaries. One is what I mentioned before. You have a radio jet that is associated with the binary. The base of the jet is eventually, instead of having a just straight jet, is wiggle jet. I talked a lot about periodicity, of course. Jesse talked about the spectral signatures. We could have the case if we have very precise astrometric measurements, because the binary is moving back and forth, that we would see the photocenter of this moving back and forth. And of course, we could detect gravitational waves. Now, the challenge here is that if you look at any of these signatures individually, none of them is unique. And in practice, what that means is that, yes, some of these candidates that I already showed you, if you look at their multi-wavelength data, you can convince yourself that they have additional signatures. Maybe their multi-wavelength behavior looks like a relativistic Doppler boost, or their jet has something weird. But then if you make a control sample and say, how often does a typical quasar produce that signature in low quality data, which is what we typically have, the answer is quite often. It's very easy to confuse each individual signature with the typical quasar behavior. Now, of course, I talked a lot about the challenges. A brief break to see if you guys have questions, because I want to go to the more optimistic message, which is the future and the great data that we will be having soon. So if there are questions, I can take a break and see if I can answer them.
I don't think we've got any questions at the moment, Maria.
Okay, sounds good. So let's talk about the future then, which is very exciting because we will have amazing time domain data very soon. And the first will be from the Rubin Observatory. There's a lot of excitement in the community. You've probably heard the news that Rubin started. It's been less than a month. It also had a rocky start because the site in Chile flooded and it has been a bit of a disaster, but it started collecting data. It has a bit of a downtime now, but it will go back on the sky very soon and it will observe for 10 years. And last year we had the chance to see this first look image that looked, we got just a sneak peek of the quality that we will get with LSST. We have some data already available from the data that the telescope took with the commissioning camera. Then when they were doing the engineering run, they also took some data with the LSST camera, which they will release very, very soon. Just for people to calibrate their pipelines, see if there are any obvious issues. And then again, I said we started on June 30th. We will observe for a year. And then it will take another year to process the data. So in mid-2028, we will have the first data release with 1 year of LSST data. So for quasar periodicity searches, LSST will be amazing. So we will have 10 years of continuous operations. We observe the sky every 3 to 5 days, and there are 6 filters that the telescope is rotating between. And because LSST is much deeper than what we could currently see with the existing time domain surveys, we will reach to several millions of quasars. This is orders of magnitude more than what we had in time domain surveys like Catalina and ZTF. The maximum, I think we've analyzed is of order 100,000. Why this is important? Because, as I said, we're looking for something that is relatively rare, and we need a very big sample. So if we have a big sample, we have a chance of detecting something that is a relatively short period, so of order a month or a week. So if we manage to detect something like that over the course of the survey, which will last again 10 years, we will see many repetitions of the periodicity. So if we see 50 cycles, I think we can be fairly certain that the periodicity is real, and it's not the noise that we're observing. These short period binaries are also very, very important because they are related, talked here, most DAs and the binaries that have periods of a few years. But for LISA, the low mass end, we have the shorter periods that are more relevant. So by finding one or a population of these systems, we can constrain the rate of binaries we can expect for LISA. Now there's also another time that will happen very soon. So the Raman telescope is an infrared telescope that is expected to launch within a month or so. It will have immediately the data will become public. And in a couple of years, they will do this high latitude time domain survey, and this animation shows how it will cover this field of view. So for 6 months, Roman will cover a small part of the sky again and again, and it will collect time domain data. Roman is very deep. It goes much deeper than LSST. So it will detect fainter quasars. That probably means that it will be lower mass quasars. So again, we have an opportunity to find the low mass short period binaries that again are progenitors of LISA sources. Now, of course, we have great data and big volume data that are coming our way, but the algorithms I described, they're very low, and they cannot analyze. So we need to think how we can make our algorithms efficient. And probably the solution is machine learning. So we have started experimenting with some very simple models like random forests and XGBoost to more complicated like neural networks and so on. And we train them on simulations and then we see how they perform. And this is preliminary results from one of my postdocs, where we managed to find about 70% of the periodic signals we injected and with a false positive rate of 1%. And this is roughly the rate, and even better to some extent, than the traditional algorithms can perform. The advantage here is that we do that at a fraction of the time. So the previous algorithms that we do, for example, Bayesian model selection, they're very slow. This can analyze the data in less than an hour, like the most efficient ones. There are some heavier ones. And within LSST, we are preparing for the first data release. We decided to collect codes from several different groups and see which one performs best or which parameter space its code is optimal for. And of course, we want the codes to scale up to the LSST data set. So this is a project that started really recently. It's open to everyone that is a member of the LSST AGN collaboration. So if you have an interest and you can join LSST, you can talk to me and I can put you in touch with my postdoc who is running this. So again, I can take another short break before I get to the synergies with PTAs, if there are any questions.
We got one question, Maria.
Yeah.
Hi, I don't know if you're about to touch on this, but you haven't mentioned like multi-band searches yet. I don't know how familiar you are with it, but I'm not super familiar. So I was just gonna ask, like, are there any like signatures we would expect in like different bands, like whether it's in like the LSST survey or like previous surveys?
Yeah, absolutely. So one I didn't mention it and I don't have a slide, but there is a signature, the Doppler boost signature, and maybe I can go back to the slide I had the math. So if we go here, the amplitude of the variability, so the mini disk probably emits from X-rays to optical to probably not infrared because they are not as extended, but for sure X-rays and several different optical bands. And the amplitude of the variability depends on this alpha that I didn't mention, which is the spectral slope. And that spectral slope could be different in X-rays or UV or optical. So you have a prediction of how this amplitude should look like in different bands. And there are some quasars that we have looked at X-ray, UV, optical to see if the behavior is consistent with that prediction. And to some extent it is, but then we go back to the problem that I was mentioning here. A lot of the signatures are not unique. So if quasars have wavelength dependent variability, and that can be very easy to mix with the predicted Doppler boost behavior. And again, because you have 6 bands in Rubin, this is a test we should be doing for the candidates we find.
Thank you.
Okay, so I assume there's no other questions. I'll try to not take too much time because I want to leave some time for the tutorial and talk very briefly about the synergies with pulsar timing arrays. So, of course, you've heard this week and probably even before that week that we have found evidence for the gravitational wave background, which is a superposition of many unresolved signals. And then we expect to find one loud binary that can be detectable on top of this background. That could happen just a few years from when we get to a 5 sigma detection. These systems, we catch them a very long time before the merger. So it's not like LIGO that we catch the very final second of the merger. We catch them thousands of years before the merger. So practically, there is a binary that is persistent, is a monochromatic source. And because we expect these bright electromagnetic signatures, it's a promising source for multi-messenger observations. And there are two ways to get to a multi-messenger detection. I'll probably cover only one, even though I have slides for the other one, because we are running a bit short on time. So one possibility is to find gravitational waves. And then the same way that LIGO found the binary neutron star, and then we found the associated electromagnetic counterpart, find the host galaxy. The other case is to find candidates, for example, from these time domain surveys, and find gravitational waves that are coming from the same system. Now, the good news is that there is a very good overlap between the binaries we can detect with time domain surveys and pulsar timing arrays. So this is from a paper we wrote with Steve a few years ago. We looked at the parameter space of binaries in terms of the total mass and the period of the binary. And we looked at what binaries we can detect, for example, with LSST, if we assume relativistic Doppler, and what we can detect with gravitational waves, different sensitivities, starting from the Nanograv the Nanograv 11-year dataset, going to sensitivities something like what we would have today if we combined all the PTA data, and then maybe 10 years in the future when we will have SKA operating and we will have many more pulsars. So as you can see, we have a common parameter space where we can find both electromagnetic quasar periodicity and gravitational waves with pulsar timing arrays. And that parameter space becomes bigger and bigger as the sensitivity of PTAs increases. Now, I talked about the different mechanisms that can produce periodicity, and I told you in which cases we can link the period to the orbital period of the binary. So for example, when we have circular binaries and we have relativistic Doppler boost, the period, we can link it to the gravitational wave frequency because it's the orbital period of the binary. The amplitude depends on the mass ratio, the inclination, and so on. So again, these are properties that come also into the gravitational wave signal. And the phase of the two systems can also be linked. When we go to periodic accretion, if we have a low mass system, again, we saw that the periodicity happens at the main, the orbital period. Again, we can connect that to the gravitational wave frequency. If it's a high mass binary, when we see the hotspot and the period is, the period from the electromagnetic data is a few times the orbital period of the binary, maybe we have a tentative connection within a factor of a few. So the best case scenario when it comes to circular orbits is the relativistic Doppler boost. For eccentric orbits, again, it's the same. We can connect the period when we have relativistic Doppler boost. We can also connect the other properties in that case. Periodic accretion, we can connect the period because for eccentric binaries, it always happens at the orbital period, but maybe not the other properties. So we decided to focus on the most optimistic scenario, which is circular binaries that the periodicity is produced by relativistic Doppler boost, and explore how, if we analyze the electromagnetic data simultaneously with gravitational wave data, what is the advantage of that approach? So we can write a joint likelihood, multiplying the likelihood of the gravitational wave data and the likelihood of the electromagnetic data, and analyze the data as a multi-messenger data stream. And here is an example of one such simulation. What I'm showing is we have produced light curves and analyzed the light curves alone. The same binary would have a detectable gravitational wave signal, so we can analyze the PTA data alone, and then we can also analyze them as a multi-messenger data stream. And you can see in a lot of the cases, the parameter constraints we get with the multi-messenger approach get much, much more tighter than when we analyze each signal individually. Another thing that was exciting to see is that typically when we do this type of targeted searches, we detect a candidate, we get the properties from the light curve, the period and other properties, and we use them as priors for the gravitational wave analysis. It turns out that doing the joint analysis approach gives us better constraints than this approach. So this is quite exciting. And I'm going to skip the second way of getting to a multi-messenger detection, which is finding gravitational waves and then finding the host galaxy. I can summarize this in 2 sentences. One is that we have a chance that this will happen in a few years. The binaries we have a chance of finding are very massive and relatively nearby. That means they will live in very massive host galaxies that are bright to be detectable in electromagnetic surveys. But the localization area is very large, hundreds of square degrees, and with that localization area, we have thousands of galaxies. So that's going to be a very challenging thing to find the host galaxy, and there's a lot of work in progress. You may have Paulina there, who is an expert. You can talk to Steve. You can talk to me afterwards, but I will leave you with the summary here. See if you have any questions before we can move to the tutorial.
Right now, let's get Maria around. Was there anything? Levi, you've got half an arm up. Is that a question? No. Stretch. Maria, I think there are no questions for right now, so we can segue into the tutorial.
Yeah, and I'm not sure how we should run it with me being remote. I know you've uploaded that on the GitHub. So my idea was that you guys work through it and I stay online in case you have questions. They're relatively simple things on how like a light curve looks like, how you can generate a periodogram, a bit on the red noise and things like that.
Yeah, that sounds good, Maria. So it's up on the GitHub. It's included in the week 2, day 3 directory. I imagine there's no specialized software or packages needed for it.
Yeah,
Okay.
no, everything can be run just on, yeah.
All right, so maybe if people have questions, they can come up to the front and ask Maria anything about the tutorial notebook or put it in the Slack channel.
Mm-hmm. Sounds good. I'll turn off my camera, but I'll be here.
Yeah. Thanks, Maria.
Thank you.
Anybody have issues finding that or moving it up? It is.
Hi, Maria. Can you hear me?
Yeah.
I'm looking at your paper.
Mhm.
I don't know if I think I can show my computer. This plot.
Yeah.
Why is there a vertical cutoff for all of the PTA stuff at like 100-ish days?
Oh, we probably so there's probably a little more because the minimum frequency goes to 2 weeks. But I think if you look at the sensitivity curve of PTAs, there is a minimum and then it goes much worse at high frequencies. So we decided not to include the very high frequencies because it's unlikely that you will find a binary there. So we set the threshold at the minimum frequency.
Thanks.
Maria, I got a quick question.
Go ahead.
So thinking about systems that are closer to merger, just looking at it from a statistics point of view, it seems like it'd be more like an easier problem because you're moving at faster speeds, so the Doppler boosting is greater, your period is shorter, so you would get more cycles. But it feels like a little bit of a scary problem because I don't know, the two black holes are so close together, it feels like their accretion is more linked and like things like the damper and Mach or whatever stochastic variabilities in the accretion disk might become crazier. So what's the sense of like the balance of the periodic signal and the accretion that makes that problem graphable?
Yeah, so there are a few things. One is you may get to a regime that the mini disks are truncated. So they may emit in the X-rays, but maybe not in the optical because they are not as extended. For example, it may get to the point that, yes, there's a lot of interaction because they're maybe, even when they are not truncated, they're very close together. So there's a lot of back and forth between the two mini disks. So their luminosity is changing quite a bit. This is a long-standing problem, whether the binary, and it's more on the LISA side, right? Whether the binary can keep the bright electromagnetic emission all the way to the merger. And there's no solution, right? We don't know the answer to that. The other thing I would say, yes, in terms of statistics, it's easier to find a shorter period binary than finding a longer period binary. But in terms of population, you spend much more time at the longer periods. So you have many, many more systems at the longer periods than you have at the short periods. That's why LSST will be very important because you get this huge population. Now, where is exactly the sweet spot of us being more sensitive to the shorter periods, but the population having more at the longer periods? We're actually working to quantify that. I would think it's at the few months time scale rather than days or weeks.
Thank you.
Okay, sorry.
Hey, Maria.
Hello.
People have had a chance to at least make good progress on the notebook. So I think we can wrap up this session and take a break before moving into Nima's topic later on. But thanks again for taking the time and doing all of this work. I really appreciate it.
Thank you. If anything comes up, just message me on Slack.
Let's please thank Maria again for her time. Take care, Maria. Thank you.
Thank you. Bye.
All right. Let's settle in for another lecture and tutorial. This time, Neva is going to tell us all about how we can do population inference, that is understanding the nature of the supermassive black hole binary sources that likely make up a gravitational wave background. And you'll have an intro to some specialized software, which is his software. And I think you've got updated software from UV to do that. So, Neva.
Okay, one thing before I begin, so I was gonna write a lecture note for this, and then as I was writing, I realized I'm just redoing my own paper again. And so I just said, why not send you guys my paper, because that would be just the lecture notes. So what I'm going to go through, we're gonna have a Jupyter notebook, and I'm gonna run you through that. But first, there's some basic stuff that you may already know, but we'll go through that. To establish some baseline for like the theory of what we're doing. So this is a paper. The thing about this field, like the population inference in pulsar timing, in North America, there are probably 4 people that know how to do this. And I'm one of them. So it's finding something that I could just share with everyone is very difficult, because people, what they are is they are either interested in the astro side, source modeling. They do not care about anything else about the detection of whatever they're modeling. Or people are all the way focused on detecting something without realizing what the source should be. Very few people know how to connect these two, and I've been fortunate to know people that can do both, and I've learned from them. This is very important. I want you guys to also be able to do both. You can't just do astrophysical modeling, ignore everything about what is possible with pulsar timing, and you can't just do gravitational wave detection without knowing what you're doing. So hopefully by the end of this lecture, you'll have an idea how to connect these two things. What we're going to be doing is looking at a population of supermassive black hole binary. It's not 1, it's not 2, it's not 3, it's many, sufficiently many. Whatever you want to call population is at least more than 1. But it's describing the kind of like an average behavior of things, if you would like. You've heard enough about how to model a single continuous wave, but this is more like how different single sources combine into creating a gravitational wave background that you can observe. So I'm gonna skip over the motivation section of the paper. I think the motivation is pretty clear. We've found an evidence for gravitational wave background using pulsar timing data. That's good, but what does that mean about the universe? It's nice to look at the corner plot, but the corner plot and the amplitude and the gamma on its own doesn't tell you anything. So you need to be able to connect what is detected to some models of supermassive black hole binary, to some models of galaxies, in order to understand what this data actually means. That's the whole point of physics. We are not data analysts. We just want to understand something from physics. So that's the motivation really for this sort of branch of pulsar timing, pulsar time data analysis and theoretical work. And the most important equation when you're talking about population inference is this equation 1. This is a characteristic of strain. Now I talked about this last week, and I'm seeing some of the stuff on the board. So I know some of you know what this is. This is just the nature of this quantity is a variance. This is a variance quantity. It's describing how we model this single sources together to describe the gravitational wave background. So in this equation, H sub s is the instantaneous strain of single sources. So strain is like the strength of a gravitational wave signal, is how much it can stretch the fabric of a space. And it's usually in this field quantified with the strain. So you have the H sub s. N is the total number of sources. If we've got more than one source, so The capital N tells you how many sources you have in a particular imaginary space in the universe. F is the frequency you observe, not the frequency of the black holes, the frequency that you see. Z is redshift, always is. And theta are just some generic model parameters that describe the sources. Theta could be total mass, could be mass ratio, could be anything. Generically, I just call it theta, and it has length p. That's what that p is on top. So it's a generic model, parameters based on some model, we'll get into later. It has a length of. And you just add them together in quadrature. Why? Because this is variance. If you want to add variance of a stuff to it, you never add variance in linear. You always add variance in quadrature. So that's pretty much what equation 1 is. You've already sort of in sub-holodeck, you can go and see how this is done. It's never done in a continuous integral form. It's always done in a discrete sum. So you will see all the instantaneous strains are calculated in the software and they're just added together using a discrete sum. But theoretically, people write it as an integral because integral is much nicer than a discrete sum. Okay. Equation 2 is something that you should all be familiar with because this is the simplest model for a black hole, for a supermassive. The orbit is assumed to be Newtonian. The orbit assumed to be just what it is, circular. And this is a characteristic of strain. It was, I believe, found at least the first time I've seen it in that Hithorn paper that is referenced there. That just gives you a simple equation to calculate the characteristic of strain if you want to make those assumptions that the binary is circular, that the orbit is Newtonian and such. Which is in the band of pulsar timing, it's very good approximation. D sub c is the co-moving distance, and m sub c is sharp mass. And this very famous thing in pulsar timing data analysis, this sort of a sub c as a function of frequency following a power law comes from this equation. So if you combine equation 1 and 2, you get this power law. And that's what we've been chasing for many years, just seeing this power law. So this is the origin of it, if you were wondering where that power law came from. Now, I could have ended the lecture right here. This is a supermassive black hole binary population analysis, and I could have ended it here, and there was really nothing wrong with it. But this is too simple. And this is a lot of astrophysicists' problem with these models that you see in equation 2. People don't really have that much of a problem with equation 1. It makes some assumptions that I'm not going to get into, but equation 2 is the place where a lot of people have a lot of problem because it's just too simple. They want to understand more about black hole binaries. So equation 2 isn't necessarily wrong, it's just too simple. So we've got to make it more complicated. For example, in equation 2, there is no point that you can see the lifetime of a binary. You cannot see anything about the galaxy that these binaries were in. You cannot see anything about how fast the orbit shrinks. You can't see any of that. It's all been included in that spectral index and whatever amplitude, because h is proportional to f, it's not equal to f to the power negative 2/3. So whatever the constant of proportionality is, everything is kind of there, hidden. And we don't like that. We want to model things as explicitly. So that's the whole business here. So let's do that. Let's make it more complicated. So there are two aspects to this. You first need to explicitly model the physics of a two-body system with the complexities of that two-body being the supermassive black hole binaries. That's one side. The other side, you need to model how many there are. So the number density of supermassive black hole binaries in your universe needs to also have an explicit model. So two different things that need to be combined to make this more complicated, more interesting. Equation 3 here does the physics. It describes the shrinking rate of this supermassive black hole binary. So B is the semi-major axis. So if you have an elliptical orbit, you can always define a semi-major axis. If it's circular, it's just radius. Pulsar timing reserves A for Fourier coefficients. That's why I'm using B here. So in mathematics, B is actually a semi-minor axis, but I'm using it as semi-major axis here because A is Fourier coefficients. So the notation, warning. T is time, so I'm trying to describe the rate of change of this orbit, equals to a normalization constant, h sub b, I will get to what that is, multiplied by sort of a two power law behavior. So you can see in equation 4. So there's a gravitational wave only side, which is something that is constant. But there's a more interesting side to this, which is like how does the environment of supermassive black hole binary affect this two-body motion? So it's not an isolated two-body anymore, like what we assume in equation 2, some other stuff that are affecting the physics and how things get close. And that environment is described by a two-power law. This is just a model, by the way. You can describe it based on if you have a favorite model that's different, this is where you put it in. But what this one does, it just tells you that there are two distinct stories to tell. First, before binaries get closer to a certain point, which is quantified by this B sub C, they shrink with a different rate. And once they pass that threshold, they change this rate. That's all this equation 4 tells you. The BC is that critical distance, and nu parameter is the shrinking rate kind of thing. So nu inner means their black holes are very close, so you pass this threshold, and nu outer is outside that threshold. Be careful though. Not everything that you want to model supermassive black hole binaries with is going to make sense for pulsar timing. Remember, the frequency range that we have is nanohertz. So if you can put the model here and you can indirectly perhaps infer what those parameters are, but always know what you're doing. You're in the pulsar timing data analysis. So just be careful here. But here's the model, right? This is how the model is completed. This is what was used for Nanograph 15-year data set. This is part of a bigger model that is called PHENOM, short for phenomenological model, that we use to constrain the population of supermassive black hole binaries. This is what we assumed the form of the physics is. The outer was fixed to a single value. I don't remember what that value was. But the nu inner was a free parameter that we decided to see what it is using our Nanograph 15-year data set. All right. Now there was, there is another parameter that is interesting to us, and that's the lifetime of the binary. So depending, there's a reference time that you define. And until the binaries merge, you want to know how long that takes for the binaries to merge. And it's usually measured in gigayears. And that's another thing. So if you integrate this rate of time over some reference values, some initial semi-axis value and to the end semi-axis value, you integrate that, the inverse of the rate, you get something that has a unit of time. And that unit of time is the lifetime of the binary. And this is another thing that was interesting for us. That's why we put it in our model. So now we've introduced two things that was absent in our power law formula. One is the rate of change, this new parameter, how fast the orbit shrinks, and now this is a lifetime of the binary is also included. Yes.
ISCOs.
That was the innermost stable. Yeah, correct. Innermost stable circular orbit.
So is that, before we go to the, faster shrinking number?
No, this is. So this is why you are in the fast shrinking region. This is you pass the critical semi-major axis.
Is the in it outside of the critical major axis? Or is
Very
it-
good question. I assume it is. Not sure, but I think it is. It's very arbitrary, by the way. It depends on your model. Where do you want to put the reference?
I'm guessing that the in it would be for like the initial, so like where are you starting your evolution? And so that's
Yeah,
just, that's.
yes.
that's-
It could be when you pass the threshold, exactly when you pass the threshold.
Okay, well, it's not work if you set it, outside of the threshold as well.
There is no constraint for that. Some people, well, if you're explicit, the in it could be zero and your zero could be defined any time. It doesn't matter. As long as this dBdt is for the specific period that you define, then you just change the definition of how to whatever you like, whatever part of this you are interested in. So we'll get to this, but this is different than the galaxy merger time. The galaxy merger time is the total thing. It's like how these are very far away, they get closer and they merge. This is not that. This is like very much, okay, where do you put the reference and the final is fixed. So this is like very much arbitrary to what you want to do. Different than galaxy merger time.
And because we're using this as someone described in relationship with background, we're looking at the innermost stable circular orbit because we don't want it to merge quite yet.
Yes.
Yes.
Yes,
Thank you.
that's what I'm saying. Remember what you're doing, what data you're using. Lisa, a different story. This is also time. Okay, that's it. Now, this is a very, very simple model in the realm of people that are interested in source modeling, even though it looks a little bit nasty. It still is very simple. Now, people have things that need 31 parameters to describe what's happening. This is a simple one, doesn't need that many. Okay, now we kind of modeled the physics a little bit. Now let's model the number density of the sources. You are all physicists, so I'm hoping you've seen a splitting of the differential of a differential fraction before. Mathematicians would get a heart attack if they see something like this, but physicists do it all the time. Because things are always okay to do. They're always smooth and continuous and blah, blah, blah. Even though n is in a discrete value, but who cares? This is physics. So what you do is number density is with respect to the total mass m, mass ratio q, redshift v, and log f. Let's split this. So in 3 fractions. And that's exactly what equation 8 is. You just split things. Now, why? Well, because these things have a meaning outside pulsar timing, and we want to borrow stuff from the literature to put in our model. For example, this splitting, the last sort of the product of the last 2 fractions, dv dt, dvc dz, that has a meaning in astrophysics. This is like how fast your co-moving volume sort of shrinks or changes. And it's very much related to the redshift and your co-moving distance. So that's why we split it like that. So because we know that's like a quantity that is very much defined in astrophysics. DTD log F is the amount of time that supermassive black hole binaries spend emitting at a log frequency. That's also something that is related to the shrinking that we were describing. That's why this is also something that is explicitly extracted from the differential fraction. And then we split this even more. So one of the terms, the first fraction we have, now we split it in 3 ways again. Why? Because these things now have a very well-established meaning. If you split it the exact way that equation 11 tells you to do it, you get 3 functions. One is a galaxy stellar mass function. The other one is the pair fraction function, and then the merger time of galaxies. These are things that are observed, measured, worked on in decades by people outside pulsar timing. And we want to use that information in our models. That's why we do it this way. We can't just go say, oh, number density is just a free parameter, and let's infer that. This is a much better because it's informed on our prior knowledge of the universe. So that's why we do it. Now, this galaxy stellar mass function is it's like the number density of galaxies. It quantifies that. So it's how many galaxies you have on what mass. This is what galaxy stellar mass function describes. And these things are rabbit holes. People have different models for it. There's a lot of data about them. So you will have people disagreeing on how they want to model it. We modeled it in nanograph 15-year, like equation 12. Again, another like power law looking or exponential looking function. It's just we use what was common in the literature. It doesn't have to be this way, but galaxy stellar mass function follows equation 12. Don't get sort of confused about the different parameterization of this. This is not important at this stage. Just know that the galaxy stellar mass function enters our model that way. Then we have the galaxy merger time, also important, and the pair fraction function as well, which is just simply a function of redshift. Was also included in our models. For nanograph 15-year, we fixed the galaxy, we fixed the peak pair fraction and the merger time of galaxies. One, because we didn't have computational resources to model everything freely. And let me tell you, beyond this, the computational problems have been resolved pretty much. My software does this very well. The problem is no longer about the computational problems. It's about these things are completely degenerate. You have hundreds of parameters varying over a free parameter space. They all try to do the same thing, and you don't understand any of them if you vary all of them simultaneously. If I tell you sum of 100 numbers is 1,000, could you guess what those 100 numbers are? But if I told you sum of 2 numbers is 1,000 and those 2 numbers are integers, you now have a much better idea of what those 2 numbers are. Exactly what's happening. Over-parameterization physically makes sense. From a Bayesian data analysis point of view, it doesn't make sense. So be aware of that. Increasing the number of model parameters doesn't necessarily mean you're doing a better job. Or you're more agnostic, doesn't mean anything. Finally, we have this Amon-Bolge relation. I haven't talked about really the mass of this supermassive black hole binary, but it's a very important thing. Mass of supermassive black hole binary determines everything pretty much, not everything, but determines a lot about the gravitational wave radiation, the strength of it at the very least. So how do we sort of model the mass? Well, we look at the mass of the galaxies, especially the stellar bulge of the galaxy, and we sort of connect that mass to the mass of the supermassive black hole that's at the center of that galaxy. And this MM-Boltzmann relationship does that. So there are observations about the mass of galaxies, and you relate those observations to the mass of the supermassive black hole that is at the center of this galaxy. This is very empirical, by the way, this relationship. I'm not sure theoretically motivated, but it's very empirical relationship. And you can parameterize it in any way you want. We decided that we want to we want to put a noise in there, so that edge that you see is a bit of noise added to the relationship. So we varied that noise, and also I think we varied, yeah, that was it. The important thing was the noise that we were finding there. I counted, this model Phenom has 31 parameters. All of that combined, and it's the simplest, by the way, simplest model. A lot of things that are kind of too oversimplification. For example, the lifetime of a binary, each binary has its own lifetime. But we don't do that, we just assign one lifetime to the entire population. So we had to do these simplifications, and still we have 31 parameters. We only varied 6 of them. The rest remain constant. Now, read the last chapter of this paper, and it's going to tell you that even that was too much. Even having 6 parameters was too much. We can only really very much understand 2 of them anyway.
What do you mean by that?
Bayesian statistics hate astrophysical modeling. That's what I mean. So you have all these things, even with the 6 parameters, you give it a prior, you get the prior back. Whatever you do, you can have an extremely accurate pulsar timing data with pretty much 0 white noise. You tell it what the MM-Boltzmann parameter prior for the noises, for example, the MM-Boltzmann parameter, you get the prior back at the end. The posterior is identical to prior.
Even when you were holding all these parameters,
Yes.
that you didn't recover anything, didn't understand?
Yes.
Well, that's frustrating.
Yes. So the idea is that pulsar timing data isn't good for all of these. It's good for a subset of them. And the conclusion of my paper is that it's good for parameters that describe the dynamics of the physics. So the lifetime you can constrain very well. You don't get the prior back, you get the posterior. And the shrinking rate, the way it is modeled, that's also very informative. Everything else, you get the prior back most of the time. So not very much anything to learn about galaxy stellar mass function using pulsar timing, not much anything to learn from this MM-Boltzmann parameter, but that's okay. Because we are in a multi-messenger system. Pulsar timing is just one piece of the puzzle. You have other experiments to constrain galaxy stellar mass function. You don't need pulsar timing to tell you what that is. Yes.
Probably missing something, but isn't the shrinking rate and the binary lifetime same?
No, one is the integral of the other. They're not independent, but they're not the same. Now, it doesn't mean that someone can find a quote unquote better astrophysical model and maybe will not have the problems that I describe in this paper. I don't know what those models are. I don't have access to them. But if you reparameterize a model where there is a lot less degeneracy, maybe there's a hope for other things. But the way we do things right now, you can really only constrain meaningfully the dynamic physics of supermassive black hole binaries, which in itself is good. Like this is, we spend a lot of money and we want to understand those things. And if we can, then that's very good. Okay. There's another section that goes over the data analysis side. I'm not going to go through this, all of this, because this is what I talked about last week. What I want to show you is the prior. So in addition to the priors that I talked about the Fourier coefficients and so on and so forth, equation 25 show you the priors that were used for nanographic linear data set. We have 6 parameters in our model. Tau is the lifetime of the binary. So it can vary from 0.1 gigayear to 11 gigayear. That phi 0 is the parameter, part of the parameterization of the galaxy stellar mass function. That's a normalization of the galaxy stellar mass function. It has a normal prior. Why? It's because it is informed on a bunch of other experiments prior to pulsar timing. So they did these things, they have some measurements of this parameter psi 0, and we took those measurements and we used them as prior. Definition of a Bayesian data analysis. You have some prior information, you use that prior information. It is a very bad habit in this field that everyone always assigns uniform prior to everything. That's not good. You're not being more agnostic. You're not doing anything better. If you have a prior, if you have this body of literature, experiments telling you what phi should be, and those experiments are completely independent of pulsar timing, you should use that data. Then this on to the end, psi 0, that's another normalization of the galaxy stellar mass function. Don't worry about them. You're curious, read the paper more carefully, it will tell you what those are. Mu and epsilon mu are parameterization of the MM-Bose relationship, and mu inner is that shrinking rate. The only parameter that has a unit is the tau parameter lifetime, which is in gigayear. Everything else is like an index or a normalization constant. Things that we have no idea what they are, we assign a uniform prior, but everything else, they have like a normal, approximately normal prior. That is it. Someone asked me 2 weeks ago about, can I have more than one marginal prior? There you go. Yes, you can. These parameters, are, at least in our model, are assumed to be completely independent. So all you have is the product of those priors. And I can show you. Yep. Look, the prior total is just product of equation 25. I don't explicitly write it out, but that's what it is. Oh, it is equation 24. Sorry, I missed it. That's theta. Do you remember that theta from equation 1? There it is. That is pretty much it. If you are interested in, I highly encourage you to read this paper, and I do a bunch of data analysis on simulated data, and I come up with this conclusion that not all the parameters can be constrained using pulsar timing, even under the best of circumstances. What I would like to do now is show you the notebook.
Recording in progress.
Okay. So this is Astro Inference from A to Z. This is how you actually do this. I've seen you guys struggle a little bit with holodeck and to an extent normalizing flows. I cover all of that here. So hopefully it will help. Hopefully it's not too late. Let's do that. So I'm going to be using PyTorch. So this device means, is it going to run on GPU or CPU? If you don't have a GPU on your computer, just call this CPU and you're going to be fine. So I have a GPU, so I will just call this device CUDA. That's all it is.
You can.
Yes, I can. Thanks for reminding me. The plotting settings, these are my preferences, whatever. Okay, let's create these priors. So I showed you a bunch of equations for the priors. Let's create them. Let's sample from them. So 6 astrophysical parameters and 5 frequency bins. Why 5? Because Nanograph 15 years analyze everything with 5 frequency bins. Why did they analyze everything 5 frequency bins? Because that was when the Hellings and Downs correlation dropped massively. So if we wanted to give us our best chance, we only looked at 5 frequency bins. Now you may say that's cheating. Yes, it is cheating. We've done analysis with more frequency bins, but the more interesting one was the 5 bin. So that's why. This astro draws is how many draws you want to make from the prior. This is actually an important quantity because holodeck's output, which is a gravitational wave background characteristic string, is probabilistic. It's not deterministic. The reason for it is because we will never be able to be sure about the number of sources in our universe. You can never have 1,000 sources. There's always an uncertainty. There's something you can never fix. So that's why, depending on how many sources there are, you get a different gravitational wave background characteristic string. So the output of holodeck is not deterministic for gravitational wave background. Now, there's a lot of work that I'm also, me and a lot of people here in Viper are involved with to try to kind of not do these things. But for now, the standard way to think about it is that there's uncertainty on the number of sources. So it will always be noise. There's always be noise. You will hear the Poisson noise. That's what it is. That's why it's not deterministic. So this number at least should be 1E4 because you want to know how this variation works with different combination of astrophysical model parameters. We use a technique called Latin hypercube sampling. What it is that it's a quasi-Monte Carlo sampler, and it's a fancy word for saying that you get better coverage. If you want to draw something from a uniform distribution, you can try it in NumPy. Just do numpy.random.uniform and draw 1,000. Look at the histogram of it. It will never look this good. It will be patchy, it will be baby. Why? Because 1,000 draws wasn't good enough. You should have given it more. If you give it 1,000,000 draws, you will get something that looks like this. Quasi-Monte Carlo algorithms try to emulate that regime of very many high number of samples, but with lower number of samples. So 1,000 draws from a quasi-Monte Carlo draw, a quasi-Monte Carlo sampler, it's going to give you the coverage that you would get by brute force like 10 to the 7 number of samples. They're very clever. A lot of clever people in the history of mathematics worked on it. So that's what it is. It's just very clever ways to have good coverage for your distributions. And this is the prior. It is exactly what you see. And we would like to save those samples because we need them. Now let's ask Holodeck to generate samples for us. This is a very caveman way of doing this. Because for about a year and a half ago, I had no idea how Holodeck worked. This was my understanding of how Holodeck worked. It looks like there are a lot of wrappers for these things now in Holodeck, but I just do this manually. What it is that I have all those 31 parameters manually coded here, and I tell them what the values should be, just manually. That's it. So you can see these are the default values. These are the things that will never change. For example, the galaxy merger time normalization will always be 0.5. It will never change. Another important aspect of holiday. It creates a grid. And you calculate things on a grid. This grid is total mass ratio, and redshift on that order. So it's you have a bound for total mass and mass ratio and redshift, and you tell Holodeck, create supermassive bifold binaries on that grid for me. That is very important. This is the heart of how Holodeck works. I am trying to change it, but for now, it's how it is. It's a grid. You can imagine, so if you have 30 multiplied by 30 multiplied by 30, a lot of samples. It's a lot of grid coverage you need. If you increase that number to 100, you better have a cluster. So have mercy on your laptop. This number of loudest sources, it just means Holodeck will not sort the sources based on like loud or not loud. Pulsar timing duration, I don't know why I have 20 years here. You should put 15 or whatever you want. Number of frequencies, as we said, is 5, and the frequencies we're interested in are those. It's harmonics, so 1 over T-span, 2 over T-span, 3 over T-span, doesn't have to be. You can make it as fine of a grid and a frequency as you want. I'm just doing a simple analysis here. And there's a lot of discussion about what these should be, but for now, let's keep them as harmonics. I don't know why function I write, I just call it do it. This is called do it. What does it do is it draws sample from this nice corner plot that we made. And it gives those samples to the Holodeck model, and the Holodeck model probabilistically again outputs something. That something is a string. That's what this do it function does. Now, because we give it a grid, some of those values of total mass ratio doesn't make sense for the model. That's why you get a characteristic strain that is sometimes 0 or infinity. So be careful about that. That's why I mask those things out. A lot of combinations of parameters that are in your prior just doesn't make sense, but you don't know it until you try it. So what I do here is in this function, I map things that are infinity because infinity strain doesn't make any sense.
Even do you think we're at a pause point?
We actually are. It's a good place to pause. Let this run. This 20 means you will get 20 outputs, 20 for every combination of, or every 1 in 4, you get 20 different realization of the background. I use a package called joblib, which runs these things in parallel because Python doesn't do it natively. So that's what joblib is. Every single thread in your machine is assigned to do 1 realization of background. So if you have 20 threads, which is cores multiplied by 2 if you have Intel, then you're running 20 of these in parallel. This is just help you get things done faster. Now you've got characteristic of strain. We'll come back and see what we can do with this generated characteristic strain.
All right, so we take some time for lunch. We've got tacos, the same as last week. So 30 minutes?
30 minutes, yeah. There's not much left, but maybe another 15 minutes left.
Okay, let's take 30 minutes to grab lunch, and we'll come back 12:30, to finish this off.
I specifically stable CPU driver. So, here, put CPU in the box. I don't know why this gave me this.
Does it show you big? Found no NVIDIA driver on your system, please check control NVIDIA. Could you control F and do good on there, please, and save that Is there?
It is.
Ah, there you go.
I haven't, but
How dare you?
I'm sorry.
I feel like we meet. Stack. Everyone's software. Consistent. Everyone's thirty. Well, all of them, the rest of them, for 30. So, you guys, we don't call it. No, it's fine. You're going to, we'll get shots here all morning. All you're generating. And then I go coupons. So, don't moderate your. You, get out if you're not. It is valid, like, we're walking around. It's not. And you create a multiplier. That was more of the barrier. Another one they did what they in the whole. Right now. Yeah. That's how we roll. And then understanding the foundation. It's just more. You know, all of it. Either larger, yeah, this is part of what. It's my quality, but it's fine. So if I don't know, you're just showing me here. Today is the parallel thing that we just. Yeah. Because no, it's literally, I just did it, it's embarrassing. I literally just sat here for an hour. For something, because it's like, I'm doing an intermediate and English function. So instead, you just, one of the ranges in parallel. I just need to figure out action, I was gonna. No, yeah.
I never paralyzed.
Because what I think it's doing is it's saying. I think it's like surrounding.
The brand, like, white potatoes. I thought you would know that they. Like they're original pop, the pop is older.
I think it's saying.
Typically.
Yeah, I think what it's saying. Well, I listen to it, it's like, this end is like zero.
Yeah.
Instead of trying to do this, instead of doing zero. Two other, basically, and it says like, okay. One equals to invest, equals to invest. So instead of doing this one, and then this, one, and then this one. So at the same time, we're gonna do this.
They're awesome.
What do you think about But farther down below where he does the.
Yeah,
I something. What I wanted to eventually found me. So, Your experience, but what happened was when we started, the same. And that first time.
I practice. And so but now everyone's lives. I mean, I just don't like this. I used to not get all tasks for the usual. I was able to see it, but I over prepared. I over prepared. It's like, yeah, it's in every.
I'm pretty sure there are different houses. Sure. Then I will. Yeah, that's what it is there. Yeah, that's funny that. And what it is a week. Yeah. Here's a red bag. No problem. Okay.
Ours is much more subdued. I will get my computer and there's very few of reading even though I understand. The longer wait way to ask questions because why do mom doesn't have this for lack of a better word. That I'm pretty sure when you back way to take it.
Right, this is not good.
Where do the
That won't be, they wish, right? Maybe, or just a very easy. Very sad. Yeah, you know, from a lake, so you, I don't need this. Over.
I don't know.
So that's what I had seen. I know it becomes strong. But there's some beauty of the idea, very beautiful. Lake, how we do, it's much easier. It's like what I'm saying, about saying, that people. So you have, they want to, we can, where. There's the like. Yeah, this. I mean, because we have like, oh, we are. From the. Yes. Ours. Sure. What?
I think the location is a
And,
so you're not.
I just, it is like. Very long. Really. My dad, finance, and everything. Really started. Part. It's like scale. Yeah. I don't know. I need something. You're like certain. Is like certain. No, I don't think. It doesn't. And I'm here. I can be wrong, preparation part of it, but. I've never really known for that. What we agree.
No.
Where didn't already. She's all sure. It's I was normally be involved with for that issue they have in and if you guys simple, you're not even national case.
I'm already low.
That's maybe. And that's one thing, I really want to say that I already see, I really teach.
I don't
know, they come all these.
But yeah.
Yeah.
Oh, you know.
Yeah, it's all business and governments.
There's one related. Now, when you are, like, I'm not.
It was really good. This one you say, I'm needed for fish.
If you're really, you take it and say, fish fry.
Every dish tastes.
There you have. Yeah, I think that's okay. We see it very similar. I love this case.
I won't know by this time. Would you say that the person is saying that, piece of thing now?
Yeah.
No.
Yeah.
Still.
Oh, all right, okay. It's such a way to make it. It's just making sure you got it. It goes over the. Yeah, and account for that. It's more certain. You know, it's not that, it's very well. Even the things are being provided. Yeah. But many people don't like sleep because it's a minute time. It's not very, much of that, yeah, but it's very, they know that. Yes, I would like it, but it's, doesn't like this.
When I see, when I went there to and I see, you sure, mayor, and for right. I start not preparing, I just, I understand you. I just don't.
I'm from the end, so many titles, I know that they're making this area. And once. Oh, yeah. Very easy. And also it's very easy to get the restaurant. It's just a restaurant. It's also. But I should say, like, there's like
And that's it. Apparently, even better.
Sure. Right, very long. I don't like this. That's why we don't need that conversation. My face is like normally don't have all that face.
There's only one person who likes this, so
Because we didn't have time. Yeah, that's what I'm saying. You guys need. I think so. But I don't. I would try that. Don't fix it on. Yeah. It's out there. So how do you like to go? It's not. This is out.
yeah, like I said, either depends on this conversation, I think you.
Yeah.
Yeah.
I mean, that's just, that is your
Yeah, because this doesn't have it. You definitely this is the wish. Yeah. Macro, right?
Across the market.
But have you ever had like a sandwich just you want to be able to
I had said something to the parents.
Yeah, that's not.
I had said it to, it was like originally none, and now I said it to 0. At some point, and I meant, I'm rocking with that. And, sorry. And so then I finally realized that when that variance did, because I didn't know what it meant, and then I finally read it. And just, it's like if you do the requirements. Very nice. And I said to the parents, I said that we made a summer. So, yes.
Yeah,
I guess you took it easy.
Yeah, you say that. And how about? These are, I was even simply have another like that. They're kind of set up with other things they know. And then I did like you. They did have all you like the ones that are so and then you. Like that, he pauses all the time. But then he did.
She really liked the surface. So.
Yes.
Yeah, I saw it when.
This.
It's like a homage to, they were like albums from the 80s, like stressful like that, and then it froze. And so these are his gear, so he turned it into like those. So all the kids loved it. All. We're gonna do some of these on, now like actual employees.
Sorry. You guys, I is giving the best reactions ever. I showed you the crowd.
Last year. Well, this is for a crack lab. And maybe you have regulation on Saturday. You should. I don't know if that is actually.
I mean, like, the script is on the bottom, the same. But like, I don't know how.
You're not even being pressure, and the auto passing causes the evacuation. That's all crazy. Okay, the person we actually tried, yeah, it's not that side. Like I said, the acceleration of it's. Yeah. Good. I had it. I'm sure. Oh, it's like. Why do you know? That's really a place you
Would just take the body and this class of multiple.
No, the existing, like, yeah, it's still alive. And it's already.
But it's like. Yeah.
There's one that is channels that, yeah, that is, it's with, you can have, some of this. Any rates that build on the, you can have some issue, yes, so we had it, so. And people use it. Oh, okay. So. And for this, back to conscious, they say, it's just something. I think I see. Yeah.
So we're not one of the really that any quarter. And that's she was still they got to offer to and she doesn't tell me what we need. He's already internet there. So it is they have a fish and he goes to their
I think, sure, just because I figured, I know, I'm defining a function, and I basically wanted to check a flag. If that flag is true, I just want the function to like break. I don't want to return anything, I just want nothing to happen. Return none. Return none, or return, just return. Okay.
That's not a good practice, since you asked.
Would return,
Don't do that, you always return something,
yeah,
but you return maybe none.
I'll see if that doesn't break.
Yep.
Are you getting it to shape again?
Huh?
Are we getting started again?
We can, yeah, I don't have much, it's another 10 minutes, then I will leave you to continue.
You just go, you click settings in the bottom. I don't know.
Is it in file?
I think it's just in the bottom left. Oh, over there.
Oh,
Yeah. Yeah, it's under
that's
there.
very covering.
Oh. That makes it harder. And then it's just.
Let's wait a couple more minutes, then we'll continue. Okay, I think we should continue. If you look at this notebook, you see a lot of places where I am just using some obscure Python packages to make my life easier. If you've never seen it, just look Google and see what they do. The joblib is something you should know how to do. Because you should never have, not never, you should avoid for loops in Python as much as you can. Vectorize your code, or at the very least, just do the TQDM, no, sorry, not TQDM, the joblib to make sure things run in parallel. A lot of so these are the things that aren't necessarily taught anywhere because the old Python was just a for loop, but now you can do a lot more. So you should be aware of that because you live in this century, not in the past one. Anyway, if I want to give you some estimate on how long this takes for a real data analysis, well, you've got to do at least 1 E4 times instead of 20. And that took about a day on a cluster. So it takes about a day to run this thing, but you do it once per data set anyway. So it's not that bad. Okay. Now you've got these things. If you run it, you have 0, 1, 2, 3, 4, 5, all the way to 19. These are the realizations of the background. These are characteristic of strain values. And you've got, again, because probabilistic, we have more than one. What I like to do is to combine all of these into one instead of having them in separate one. And I use a format called memory map. Now, what memory map is that it doesn't dump a huge array on your memory. It creates a path, a buffer between the map, between your system's memory and somewhere in the file. Now, why do I do this? Because in the real case, you have at least 10,000 samples for your model, and then 10,000 samples for your background realizations. That's 10 to the 8. And then you have, let's say, 6 parameters and 5 frequency bins. So you've got like 11 times 10 to the power of 8 number of samples. That's a minimum, by the way. That assumes nothing else in your computer is consuming memory, which never is the case. So you have to have a memory map. Otherwise, you will always have an issue. So if you're not familiar with memory mapping in NumPy, that's what it does. It just creates something on the file that the memory knows how to access it quickly, but it doesn't live in the memory itself. So you can technically have 10 to the power of 24 samples. You can generate them. If you have enough storage for it, that's fine. Your computer is not going to complain as long as you have a storage for it. This is the normalizing flows part. So we have samples for our model parameters. I showed you samples. We have probability distributions that are either uniform or normal. What we don't have samples for are these characteristic strains that are being calculated. So this samples of the characteristic strains will be all dumped into a file. We only have 20 of them. Those describe a distribution. If you plot them, if you go do a plt.hist and look at it, there are only 20, so you're not going to see a good histogram, but you're going to see something. What's the shape of that? What's the shape of that distribution? I don't know. That's why I want to use normalizing flow. I don't want to guess what it is. Probably inverse gamma. Because it looks like inverse gamma, but I don't know for sure. So let's use normalizing flows. What normalizing flows is it's a machine learning technique. You give it samples of a probability distribution, And it converts those samples to something that is a proper probability distribution. It gives you something you can evaluate probability of. If you have just a bunch of samples, let's say you have 1,000 samples of something. You just have samples, you don't have probability. So what do? You have two options. You either have kernel density estimates. This is something that Tempo works with. I'm sure you've seen that from yesterday. Or you have the choice of normalizing flow, which is infinitely better than KDE in almost everything, because it learns the correlation between samples as well, and it scales to pretty much any number of dimensions. This hasn't failed me normalizing flow yet. And I've gone up to 10,000 dimensions. So your response should never be KDE for anything anymore. Again, be familiarize yourself with what's being done nowadays. Always use a flow instead of a KDE for anything. It trains faster, it's more accurate, and it's better at it from every aspect. That's what we're using here. But because it is a machine, yes.
Just make sure I understand. The normalizing flow takes our random samples and tells you what the probability distribution
Right.
of those samples are, but we did not know that off.
Yeah, because we only have samples. All of it generates samples, it doesn't generate probabilities. You want to turn the samples into probability. That's what normalizing flow does for you. So please do a PLT.histogram of the samples, and you compare it to what's gonna happen at the end with the flows. One thing that is gonna make or break normalizing flow is the data normalization, and it has nothing to do with the name normalizing flow, by the way. But you've got to normalize your data before you do anything in machine learning. That's exactly what this cell does. It decenters the data, meaning that the center of the data is now its characteristic strength from whatever it was. Now it centers it at 0, and it also makes it be bounded in a symmetrical interval. Why? Because the normalizing flow algorithm requires this. So the assumption behind the code in normalizing flow is that you decenter your data and you do this type of normalization. It is extremely important, never ever skip this, no matter what machine learning algorithm you deal with. Your data should be centered in 0 and should have unit variance as much as you want, as much as you can. This algorithm doesn't necessarily need that unit variant thing, but it needs to be centered around the, needs to be bounded between, let's say, -5 and 5, -10 and 10. I'm using a package called Zuko to do this flow training. There isn't really much into this. It just transforms, it learns how to turn your samples into a proper probability distribution. I will be more than happy to, if you have a question how exactly that happens, to answer that. But this is just like an example of how you would use the normalizing flow. And we'll start like this. So if you try to understand it step by step, it's an optimization process at the end of the day. So you have these things called neural networks, and the layers of neural network needs to be optimized to understand how this transformation works. What happens inside normalizing flows is that you have a very basic distribution, like a normal distribution, and those base distributions are becoming your target. And that transformation, God knows how that needs to be done. So your neural network tries to optimize itself to learn the right transformation. It's an optimization problem at the end of the day. And these steps are the steps of those optimizations. So this is a progress bar that we're showing. So these layers of neural network are getting turned off or getting turned on. And until finally you figure out a good combination that's making sure everything's working fine. It is very much, yes.
So if I understand this correctly, each of the neural network of the node will have assigned a analytical transformation of your data.
No, it's very, so the neural network is very primitive here. They are just a fine transformation. So there are like this X plus or AX plus B transformations are happening. In this specific normalizing flow, things are a little bit different. Your neural network learns the parameters of a function that does the transformation. The function is a spline transformation. Don't worry about it. These are a little bit too complicated. So the theory of normalizing flows is that you've got to have a transformation function that is invertible. It's called a bijectors. So you should be able to go from your target distribution to the base distribution and the other way around. You can say, oh, I want that bijector to be an exponential. Or you can say anything like an AX equals B type of transformation. None of those work. Why? Because they're not flexible enough. Let's say you want to learn something that is very, very, very complicated. You can go from a base distribution to a complicated one just by an exponential transformation. So what options do you have? You either chain a lot of exponentials together, or you find a single, very flexible transformation. This flow does this single flexible one. It uses a thing called rational quadratic spline transformation. Someone in 1980s figured out that this is a very good choice for normalizing flows didn't exist, but the good choice to fit things. And it's adapted by normalizing flows. Neural network that is being optimized learns the parameters of that spline transformation. Starting from a very random nonsense initial parameter. That's the beauty of this. We don't know what it is initially, it just has some numbers, but it converges to the true values through this optimization. Now, how long should you let this go? I have no idea. You've got to have some diagnostic tools. In one of my papers, we do the sort of the Hellinger distance, like the quality of the emulated samples versus the quality of actual samples. You compare them, and you finally reach a saturation point. You can use those things. The loss function you may hear, I don't like loss function, it doesn't tell you much, but you can use that as a diagnostic for when you want to stop. Usually, if you're normalizing, if you're using a spline flow, with, let's say, less than 100 dimensions, 10,000 steps is usually good enough. But it all depends on what you're doing. Okay. I'm gonna turn this down to, I want to get something right now. I'll just do 10 steps. That's it. There you go. You've got characteristic of strain as a probability distribution. Why did we want this? Because it's a prior. Characteristic of strain now has a prior. The prior is a numeric function that is flow. Last step is astro inference. You have a pulsar timing data. You want to know what those model parameters are, those 6 model parameters. How do you do this? Well, Enterprise and all these new shiny software don't do any of this, so I had to write something for myself, which you are more than welcome and encouraged to use if you're doing it, if you're in this field. It's called Pandora. It's used to do gravitational wave data analysis, any flavor of gravitational wave data analysis. Today we are just doing the astro inferences, so that's what we're going to do. Pandora is Enterprise, but 1,000 times faster. That's pretty much it is, and more limited. But we only want to do gravitational wave data analysis. I don't care about other stuff that's in Enterprise. And it's not a wrapper, it is its own software. So what Pandora gives you is that it can accept normalizing flows as prior. So instead of telling the prior to be a normal distribution, you can just give it a normalizing flow object and say, well, use this as my prior, and it will understand how to do it. So let's load Nanograph 15-year data. You should all have access to it. It's inside the same folder. So these are feather files. These are just compressed version of Nanograph data for 15-year data set. Let's load the white noise parameters because no one wants to do reanalysis of the Nanograph 15-year, finding the white noise parameters already given to you. Since you are familiar with Enterprise, I'm showing you an Enterprise version where I'm calculating two quantities called TNR and TNT. What these are is that these have become your data. So you go from the timing data to two other things that are Pandora calls data. These are products of matrices in the likelihood. So instead of this giant time series, you deal with something that is much smaller. Okay, this TNT 670 by 670. Even though we have 67 pulsars and thousands of QOAs, that data is converted to something that is much more compressed. And Pandora knows what to do with this 670 by 670 matrix. That's it. Everything else is just telling the software if you want Hellings-Downs correlations or not. Let's say we do want Hellings-Downs correlations. Do you want uniform prior for the, it's not really, yeah, do you want uniform prior for the parameters that are not as specified with your flows or your Astro parameters? Because remember, when you're doing a real data analysis, you have to vary over a whole bunch of other crap. It's intrinsic red noise, it's this, it's that, chromatic noise. What kind of prior do you want for those? This is just says it's uniform for everything else. And really, that's it. There's this class called Astro Inferences in Pandora. You run that. And it gives you a likelihood. Look at that. Once you have a likelihood, Pandora also knows the prior, which means we can use Monte Carlo simulation. Let's do a quick timing of this. Let's see how fast it takes. Probably gonna be very slow. 43 millisecond. Reason for it is because in the actual real data, it's running on my laptop as well, which is not as strong as should be. But pretty good. I think Enterprise is the same thing, cannot be done in Enterprise, but if you just wanted likelihood evaluation, it takes probably a few hundred milliseconds. This is at least, I would say, 5 times faster. And view sample. What does it do is connects your Astro parameter prior with your likelihood, that is just PTA likelihood, and it infers the parameters of your astrophysical model that we went through. Galaxy stellar mass function, that new parameter that was about shrinking the orbit, the lifetime of the binary. It tries to understand what those should be based on your pulsar timing data. That's it. We completed Astro Inference. This is just given to you as an example in case you want to do these things. You have a model for population of supermassive black hole binaries, and you want to just know what PTA data has to say about it. I've made sure that you can do this with Pandora and everything else from the holodeck as well. There's not much else I've got to tell you. Play around with the notebook. See if you can, the most fun part is just getting the flow to maybe emulate your prior probability. plot a histogram of what is emulated from the flow and see how it looks like, the samples generated from the flow, how do they compare to the samples that you generated out of Holiday? You can do those things. And I'm here to answer any question if you have about any of this. Okay.
Images, people spend their 30 minutes working on this?
30 minutes would be fine, 30, yeah.
Just to note that the rest of the day, obviously there's plenty of talk about there, so maybe move on. But the rest of the day is also hack time. There's even more hack time tomorrow with the finish off. So starting out thinking about how you want to tie off some results, some plots, investigations, and where you want to get to by the end of tomorrow. Then you a short presentation of that, get back to the room, or representatively through the on Friday. Friday will not touch this. We have what is the best solution. It's fine. That's not.
What would you rather do? Correspondence. How general should you start thinking about it?
First thing we should do is understanding of the nation. For example, $5,000 is replacing all rules, all the walls on the area. So looking back and then have and it's good. One of five. One of the more qualifications is why another. Only one year. And you unbound and right. So you have the science. That's it, you have the all. You have to do the and but you want to do anything right, how you and you say, hey, I think I work. On, if you got it, on fire. Last generation is every point of the last from interactions, should go in interactions. Being around Okay, the next one, there has to be a motion. All inside.
So. First.
As an attorney, last meeting. Last. Every else, you were married, as I mentioned that. At very beginning, that's. This is the line. Yeah, I'm fine. So they write out the budget down. And secretary, how about, and five people. Insurance. I'll check that. What do you have? More time, you have any response? Everything was keep my own service. This is all and program. They will let them in here. Program for it. They fire them was the issue.
In this. Gotcha. So.
Once you start, it simply comes in. Like math, I think math is always presented like that. But once you manage it a little bit, because it makes the math your point. Instead of, always having or maybe. Product. Every that's what I try to and I was all of these is I mean that's my background. I thought for a while and Yes, everything goes on. Right, and it has to be, because of the American back, like, and then we're on, and you're my words, it's not your. You have, you're not. I will manage that. Now, things. And then. Jack. People. But I was saying that, and I'm not the one. I said, we're not.
Jackson face, and that inspired by the environment.
So, you don't have any difference.
I wouldn't think that should be smart. And the operation that's why you not change the shape of that area. All the anything it's how you like that.
I think
So what happens is
Well, then some
that deep bang, just resets.
all the back then.
To the previous sound.
I must say it's.
We didn't try it. Because then I found that one, and I started.
Interesting. What is
One, so that's, depends on what you want, okay?
Then deep bang already there.
Or you have two dimensions, both for
They,
so I think you have a bunch of dimensions, we go maybe instance of the way. So there is one you don't get. Yes, all. But like I go down. You think, more I don't think more. If you're right, I saw it. Why not? Or it's about my farm, you guys. It all. It's not fun, it's not a Swiss issue. Well, make sure you have it on camera.
So.
yeah.
Not so emergency, that's. The job.
Last I mentioned, well, I don't know. That's.
Right, that makes sense, 'cause I know that past one did, I passed two, because I walked it. I had 10 dogs, so I actually into that. Okay.
So you're, and all of those things. And all the tables. What is, you have, everything, but they wanted the.
That's when we hired.
You make a back dimension, so it's so. You make 5 by then 1. It's 5 by 1.
Oh, okay, but you just had.
Here's the, wait, don't pick up where the base is doing now. Remember, the complex, they're using.
I'm trying to do the same amount of so you have. L equals. Here, and that's any. And there's one. With that,
Like L1 and vortex, and it's the one L1 and my. Yeah.
Or more than, you get it. And it's not the last. So we can. Is there?
I don't know.
That is, no, that's yeah, sorry.
Always. Every iteration is. I mean, you don't have that to be.
This one is different when the first year, right? Well, I guess I'm not, you know, I'm going to
All the other. All of
So what we're asking you. Steve, but the
basically asked me.
okay, so we follow through and.
Your default, I'm running more than. And what the for the.
Yeah.
And
Thank you. Oh, is it on their roster?
One side to understand the effect.
Right. It's all under, right?
Sorry, just remote. So you mean you're in all there? It's right, you're right. Even nothing that you can find, there's a conversation.
I say that.
And at the same time, there was the word.
Yes. One.
Some of the same controls. And that's, it's just that they come here, I just think thousand euros.
And now. It's not
Simulations. Number of that. Yeah. That's what I was saying, you're not able to yet. But they can. I just saw that. Oh, yes. I think. Yeah, that's the process. Please. No. So my. It's the frequency of the. But you look at it where. Right then. Okay.
So, I'm very sure you make it. This is fancy. That's maybe over. That I mean, I could be wrong, but it it's probably more than that. Yeah. That may go back. I mean, does it have like? There has to be some remote way of space
Yeah.
If they're really like, probably transition, but I mean, we say it's secret. Because those things can be very loud and sound. And even if they're online, it's like over them. That can be my place as well. Yes.
Then remember that all that.
All of But we really so this and we'll look around. I keep time, but you like to record them. This one will probably be. I don't Like that's what I'm saying, even the episodes of Mars.
So that's what it seems.
But partly you're big.
Yeah, I'm saying all of
Well, let's see here. Oh, yeah. What do you think? Well, I said, okay, yeah. It is like, you know. I will say that you try to hold your own forever.
But you can make
So let's just try this. I think we're going to make calculate correlation. If we get years. Every time, just like I didn't access the payroll, so people are. Like I did for that condition, I should see now. Oh, okay. Oh, okay.
It's fine, I gotta go. Yeah.
Okay, 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 so we need to get the correlation. So we need to figure out how to do that. Maybe that, do we have this to be in like, thing? And that's there. We need to do this. So this is the, we have to change this to the whole services. At least for variance matrices or. Correlation for variance matrix. Yeah, so basically, are your policies the covariance matrix of your and here are data, the actual correlation. C is going to be in correlation by the correlation. And then this R is or like n pairs, it's not a question spreading thin. So this is gonna be
Oh, yeah. No, this makes sense. Okay, so this would be in here by MPace. This is in here, sorry, this is transfer, so it's MPace by impair, that's in here, yeah, impair. And then this is your correlation, which is impair. So then you also pull out that impair, so you get impair. And so that ranks the pixels by how much they look like parts of. So I can tell you that the nanograph. Then, so then, this is when we start to think about what to do with that ranking of pixels. No, and should we lighting up so that pixels one of them come out to reach some sort of threshold for how much a sky map matches with their correlation, so right, like we know which pixels are most important, and then we can simply just like put some amount of power and so basically, so like, you know, but at least at that time, we're trying to get. We're trying to minimize the chi-square between our response features and some sky map. And the sky, but the order in which we light up the pixels would be based on this rendering. So it's like kind of a way to basically like approach the thing I'm thinking about is we want to start analyzing it for giving amplitudes that don't actually improve the fit. So maybe there would be a reduced aspect to this because we're dividing by the number of amplitudes. Whatever. Yeah, chi-square for accurate freedom, I think is over the number. So then, I can see where that is saturates. So let me try and make these correlations and we can at least get to here and then you see what.
The thing is that.
So when I did this. This thing is construction.
Each of them from the date that as of that we're going to but now when this happens that great relationship then from those that are all sides that happen. As you know, all heights, now we have because you have to that so now he's angry for the south of those.
Yeah, that's
because you're scared and made here than a round that has
so I would expect.
So now obviously you are but it's not so now we're going to have that your rest in the year Which is what we said, we said that the approximation value.
So basically, these 3 minutes or this is 1 minute. And so it also looks at the I and J. Just the error bar being so big, it's on the fall, it's the. The data. Try and then you.
But you can build on to do. Is for one
Yeah.
As you change the reason, one, but you don't change that. Don't have that. Same result. One. That way.
And then just go through this. Yeah. But we do.
So that I'm saying that you know, one symbol is one that
This one is way. But I expected no, I because I could go home. It will be that. For the. Yeah, so when you said.
So when we find N90, or we do it on this product, N90. I'm very sure.
So when you have okay, so the way we put this, we are size or all that. And removing models. And we want to be this by looking at this. So the main size one is the focus. Then we decide is then 1%. So when we decide
Oh, we're right on.
Yeah, so we want to use that. There's on this one, you do the 27, so. 1307. You know exact number. So it's like, and there's 2707 will be. So in our case, you should just put in all like N90s, because we know exactly there are N90s. So we want to forward and the other ones they look at, you know exactly one.
that's.
Thinking about with is if you're hoping that's my planning zero. Yeah, to start our zero start our with like and then they tell you your pattern. We're gonna need if we around or another one sources that we and so I'm like from there, I'm not sure how we get to one and then 3. From there, you have one. And then. RW, and that way we will have many. And it's not very visible. But when we look at speakers sources, what this is like a vector of like like very go through the for
That's okay, yes, but this is. Yes, it's not saying not just counting one. And what we should say is. We're trying to do and I use now so signal from the louder we did you know that you know it's so one issue another so so I think that's a point set. Yes, we try to read. So now we have the N9. I is about so for everything you can when yeah. So saying I think that you know, if we did, like, you know, because of the rules, we don't have those. Because, I mean, you know, it's not. Like the eye. Always. Yeah. So, I think that since. So then it's going to go next year. One of the seats for. Yeah, that would be fine. This is all there. Some other and for the evaluation. Yeah. And then what's the same? Let's go. So we actually have this in 7 or 9. So sort of it's like conditions for other languages. So if you see you want to see where it is here, but it's not doing the current direction. It's cool. When also the after the current number, they were done. First time, then you go bring 67. That's what I'm saying. And then. Right. Probably. I think it's 10 to 5 minutes. Then. You have it's just the character that's every 5 minutes. Then 67 times. And that's 11 and then. What you're just you did all the rest of the year. You're in the middle of the actually, yeah, it's like that way. Yes. And you're well, I really like so each core is going to have that to be this thing, and then you get that. Like you can. Okay, so the green is very good in basket. And the first thing is a function, or very deep, the side word, and then you have like blue is in line. So that's the only thing is that. So the green, it is you can. What you can see is you should try and enjoy it. Oh, yeah, and you continue this change.
I don't think so.
Yeah.
Okay. And that's not really good.
In this case, this is memory. You want to only create one. So in that case, I can give you 5 oh, the Greeks have And then every realization. This is using, my. Yeah. Oh. I just. Yeah. So I have, let's say, just one more slide, let's say. Actually, I'm gonna do this. Let's say it's great realization. And every realization. So I guess, when I'm computing the break, which is I then want to equation, also small values that you realize. So what this brings attention going is also obvious. Oh, yeah, well, so we'll just have. If you don't have also those. Let's go for like.
In this one.
Yeah, so, okay, so with this line is.
Oh, yeah.
I'm gonna bundle this. No, I am gonna bundle it, because I know. They don't. But.
I've never used this.
This, this core is,
2707.
yeah, I'm pretty sure. Is, yeah, so, is a.
Understand how that.
Is a curve, so this is where we took all those being fixed. Timing the models, right, like that. Whatever. So it's going over the red noise parameters pretty close. The common red noise. So it's like you didn't need the correlation. Okay. And it's fixed gamma, the gamma, fixed shift. And so the optimal statistic is an estimate of the autocorrelation. And from there, it's doing and and then you can pull out the correlation.
So if you go down.
Great question.
Because like.
Okay, so the blue, I'm confident is actually be going to take all of your measured correlations and just fit them in. And you're writing it. Or a bit more. It says A squared fitting. Oh, you know what that is that's fitting for, that's saying. If HD is the temperature, I think it's like, what is the on. I think, because it's like, it's,
In this way.
there's an equation that's like x is squared, thing that's. So this is right? This is like. We know what we're expecting some spectral shape or spatial coordinate shape in the spatial coordinate. But we need to actually know how, what is this a squared is basically being able to match that matches the correlation that we observe for the pulse in the data. So right, like we have. Yeah, so it's like we have points that are like that, you know, some spread, right? And so you have some template that is like. Right, and then it's up and down. I think, but, all there. Yeah, and I agree. Okay, but we have correlates. I'm trying to actually get here from one place. I see what you're fine. Just like these guys go. Everything is all that. Oh, okay, wait. Okay, row.
And this is what I could do.
So. Watch this. Look at it.
I've got some shows, I just. Doesn't give a name. Sorry. Error that I got, but that is something I tried it and it's still. So, yes. Some here and.
Alright, so those are our big correlations. So this is why we, this is why we. This is yeah. And then the one final section. So this is maybe. Very good.
It's like, man, I don't know how I'm gonna think about it.
I mean, look, you actually don't need, you don't need, I mean, I think you just, like, I don't think we don't have.
Well, I will try it.
Right, let's see, we can just see. I mean, it's, yeah, let's, if we just.
I've done it before, like I've done this.
Right, so. It's much harder to get, because the other thing is, right, our pulsars are distributed in the galactic plane. So you have a lot that are very close together in the plane, but it's very hard to get them. We opposite, like, we're looking outside of the galaxy, way so, yeah. I think it's just fitting them and then. Yeah, this fit means you're like medium and this and that. Good. Okay, so we have correlations. Okay, so let me send you these.
Yeah, that was.
Let me make it a red.
Okay, different.
Okay, so let's see.
Yeah.
There's something else that I should go to. Yeah. I have to see that. Yeah, but it's been right. Stay very long. Yeah, but see, if you kind of see, this is, I'm guessing. It's probably actually. Yeah,
So, I guess.
Okay, let's see. Let me send this to you. Just use models.
Right, which should be good. I'll try that.
I'm saying this
They take like. But, I'm doing it in my iterations for the calculations. So I can.
It's a lot.
Do everything. It's not parallel. That's definitely. I'm happy that. It's very. But it took a lot.
Saying is. You can go this.
Oh, yeah. I'm not how you do that. Then just like a Friday, I'm very. I'll see this. Oh, that.
The answer is yes.
It still is.
I think the plan should be.
All right. It's.
It should be.
Yeah, he said.
And you say, this actually is the. He does it too, it's fine. But saying the four is a bad. So one. So that's why,
Yes, true.
It's not there.
Yeah. So you guys should. It's always a good idea. That is actually my that's one too. This Yes. You just do what you The first one is the separation. Yeah, separation. Correlation, error on. Yes.